Colour exists only when it is seen by the eye and interpreted by the brain. Natural colours, whose chemistry changes with the seasons. Subtractive colours, additive colours, dependent on the whims of light. Man-made colours, to a precise chemical standard. Different pigments, printing inks, paints, dyes of many different colours, and phosphors.
It is surprising, isn't it, how large a part colour plays in our everyday lives, although we tend to take it very much for granted. Chemistry provides us, through dyes and pigments, with almost all the artificial colours that we exploit and enjoy. Is the colour of these compounds something beyond our control? Or can we predict the colour of a molecule before it's even been synthesised? In answering these questions, we shall see that modern technology, in the shape of computers, plays a very important part. And we shall see in turn that colour chemistry contributes greatly to today's technology.
Without colour, information is limited. Nearly everything man-made has a man-made colour. In 1666, Newton showed that a prism could split white light into the many colours of the rainbow. Possibly this man-made spectrum was the start of serious investigation into the properties of light. Nowadays, we generally use a diffraction grating to give us the same effect. It gives more intense colours over a wider area. But what is colour? Yellow, for example. A pure yellow would consist of light of just one wavelength. This travels through space, arrives at the eye, and is interpreted by the brain as yellow. This is the type of colour produced by a sodium street lamp. But the same effect can be produced in other ways. This yellow, which looks similar, is in fact composed of two wavelengths mixed together, a red and a green. Again, the brain interprets what it sees as yellow. If a blue wavelength is added to the red and the green, what the brain now registers is white, made up of a combination of red, green and blue. And if the green is removed, we're left with red and blue, and this is seen as magenta or purple. And purple is the colour of this dye. The question is, why does this dye solution look purple, and what has happened to the green part of the white light? First of all, we'll demonstrate that the purple dye really does absorb green by moving it into the path of light from a diffraction grating. Well, it absorbs most of the green and some of the blue. Part of the full spectrum has been removed by the dye. How does it do it? We'll have a closer look at the solution, at a thin layer a few molecules thick, and imagine what might be going on. The purple dye molecules and the water molecules are all moving around at random. This represents one of the dye molecules. A beam of white light, which passes only through the solvent, is unchanged. But if the white light happens to pass through the dye molecule, the light emerges as purple. It's only since the development of quantum chemistry that the reason for this has been understood. In the quantum theory, we assume that light travels in the form of particles, photons. So white light can be thought of as consisting of bundles of red, green and blue photons. The green photons disappear when white light travels through the dye molecule. Something must be absorbing them, but what? In fact, we now know that it's something to do with the electrons in the dye molecule. This diagram shows just the outermost electrons, known as pi electrons. Let's imagine that we can follow one of them. As light hits it, the photon of green light happens to have just the right amount of energy to knock the electron into a different orbit. The electron acquires the photon's energy, and this is what makes us see the molecule as purple. Blue and red photons are not absorbed. If this energy was retained, the molecule's temperature would quickly rise and it would just disappear in a puff of smoke. Generally, what happens is that the energy is lost by heat transfer to the solvent molecules, and the dye molecule is then available to absorb another photon. Or the molecule may re-eject the energy as a different photon of light. This is called fluorescence. For example, in ultraviolet light, the brightener in a soap powder fluoresces. But all this, of course, was unknown to our ancestors, who could choose their dyes only from natural sources. Elderberries, for instance. Or cochineal, a red dye made from ground-up tropical insect cases. In fact, until 1856, dyeing depended on knowledge handed down through generations, and its development on trial and error. With the development of organic chemistry, chemists were to gain control over the structure of the dye molecule, and at first responded by producing synthetic dyes to replace the natural ones. Indigo, natural, and synthetic. Weld, and others, resulting in a total replacement of natural dyes. In 1895, this colour circle showed one firm's range of the synthetic colours which were then available for dyeing silk. And in order to attempt production of new colours, it became important to establish a relationship between the colour and the molecular structure. Colour also had to be defined somehow. The spectrophotometer had been developed and used to measure the colour of a dye or pigment. The spectrophotometer works by measuring the amount of light absorbed by the sample at different wavelengths. The way our purple dye absorbed the green in the spectrum can now be shown quantitatively. Most absorption occurs at a wavelength of around 550 nanometers. Let's look at some absorption curves in diagrammatic form. The spectrophotometer plots absorbance against wavelength. A complete spectrum in this diagram shows that no colour is being absorbed at the moment. But this trace shows the amount of light absorbed by our purple dye. The maximum absorption point is called lambda max, and in this case, as we've seen, it's in the green part of the spectrum. Lambda max helps to define the colour of a dye. This dye has a lambda max of 550 nanometers. The colour that we actually see is the complementary of green produced by a mixture of the colours which remain, mainly red and blue, making purple. A dye with a lambda max of 650 nanometers will absorb mostly red, leaving the complementary colour blue-green or cyan. A dye with a lambda max of 450 nanometers absorbs blue, leaving mainly red and green, and so we see the complementary color, which is yellow. The way was now set for the orderly development of color chemistry. Chemicals could be manipulated to make different colors with some degree of consistency. The colors produced could be measured accurately. There was still some uncertainty of the color that a newly devised chemical would have, but rules had been made to help chemical manufacturers in color prediction. It seemed that in predicting color, there were two main effects to be considered. First, conjugation effects, which are to do with the size of the molecule. It was realized almost 100 years ago that the larger the molecule, the bluer the color, although it wasn't known why. Secondly, substituent effects, which could be used to alter the color to a lesser extent by adding small groups to an already existing conjugated system. Using the quantum theory of light, the operation of these old established rules can now be explained. Let's consider the benzene molecule. These clouds represent the space occupied by the outermost electrons around each carbon atom, known as p orbitals. In actual fact, electrons exchange between atoms. And this means that the p orbitals overlap, resulting in clouds of pi electrons, which we saw earlier, and which spread their movement over several atoms. And it's the pi electrons which can be shifted into a new orbital by the action of light energy. Let's take a closer look at the energies of these pi electrons. The three highest energy levels of the pi electron orbitals are represented by these lines. Each level is occupied by 2 electrons. At higher energy levels still are other orbitals, which are at present unoccupied. As we saw earlier in the film, a photon of the right energy will be able to knock one of the electrons up into one of the empty higher energy orbitals. It's the difference of energy between these 2 orbitals, delta E, that will give us an indication of the color of the dye. In the case of benzene, delta E is so great that only ultraviolet photons have the right energy to be absorbed, so benzene has no visible color. It transmits the whole of the visible spectrum. However, if 2 benzene rings are linked in such a way that all the atomic p orbitals overlap, the resultant pi orbitals now cover the whole of the new molecule. This is an increase in conjugation and has the effect of lowering the energy gap between occupied and unoccupied orbitals. So a lower energy photon can be absorbed. Instead of ultraviolet, blue photons are now absorbed, and so this substance looks yellow. The pi molecular orbitals can be extended and the energy gap lowered by adding further groups. Now blue and green photons are absorbed, and so this substance looks red. Using naphthalene instead of benzene further increases conjugation. The lower energy gap is now just right for red photons to be absorbed. Here's a demonstration to show an increase in conjugation by azo coupling. The yellow coupler is reacted with a diazonium ion to increase the molecular size, so that the product, an azo dye, is red. The reaction takes place within the cloth itself, and so the dye is produced where it is needed. This is an industrial method of dyeing, but it requires 2 baths of chemicals and careful control. Nowadays, dye is usually manufactured to its finished state and sold as a powder, to be redissolved and used as needed. Or it can be printed or transferred onto the fabric. conjugation and substituent rules have for a long time been a sufficient working guide to determine the probable colour of a dye. But they cannot be relied on 100% to predict the colour of an as yet unmade substance. And they don't work in all cases. There are several well-known exceptions. And here's one: blue jeans dyed with indigo. Indigo can be considered as two molecules fused together. Taken separately, the two identical parts would be colourless. And according to the rules of conjugation, if these two colourless molecules were to be combined, they should produce yellow. And yet we know that the result is actually a deep blue. Another exception is naphthalene, C10H8, a colourless substance. Yet its formula is the same as azulene, C10H8. Each has the same degree of conjugation, and yet azulene is blue. As the chemical formula is the same, the difference in colour must be due to something else. So rather than basing our rules on a system of trial and error, we need to start at the molecular level and calculate the molecular orbital energies, using a computer to help us. Delta E will be calculated. A method of doing this for dyes has been developed at Leeds University. Here's John Griffiths again.
This molecule, for example, had not been synthesized before, but it was of interest as a possible source of colour. Rather than try to make this molecule directly, the first step was to predict its colour using this method. The first important thing to do is to simplify the molecule so that only those atoms and bonds which form part of the pi system are considered. Then we must number the remaining atoms in any logical manner. The computer then needs to know various parameters: the number of atoms, number of electrons, energy data. The first set of data describes the ionization potentials of each atom, and the electron affinities of each atom in the same order, and next the charges on each atom, which can be 1 or 2 depending on its valence state. The next set of data refer to the energies of bonds. And finally, the geometry data for the molecule, so that the computer can build up in its memory the shape of the molecule. So now I'm going to type the data in and set up what is known as a data file. This console is linked to a large computer called the Amdahl, which in its memory has the suitable program for carrying out these calculations. Well, now we've fed all the necessary data into the computer, and we can tell the computer to memorize this data as a data file. Well, this data is now filed away, but before we go on and do the calculation, it is worth just checking that we've put the data in properly. The last set of information on the screen relates to the geometry of the compound, and we can check quite easily that this geometry is correct by instructing the computer to print out the structure of the molecule based on the information we've given it. Well, now we're satisfied that the data that the computer has is correct, we can instruct it to carry out the calculation, and this will take a few seconds.
From the data given, the computer doesn't know how the electrons are distributed in the molecule, so it can only calculate very approximately the form of the orbital wave functions. Once the approximate wave functions are obtained, it can then make a rough estimate of the electron repulsion effects, which leads to a better set of wave functions and a better knowledge of electron density distribution. This process is repeated many times until no further improvement is possible. All waveforms are then said to be self-consistent. Orbital energies follow. The visible absorption band corresponds to the transition between orbital 7 and orbital 8. The difference is delta E, the energy gap. Delta E is modified to allow for electronic interactions, and we can then print out.
The printout gives us a lot of information, but what we're principally concerned with are the energies of the various molecular orbitals here. The two orbitals involved in light absorption are orbitals 7 and orbitals 8, and from these energies we can calculate the absorption energy, which is given here as 2.3742 electron volts, corresponding to a wavelength of 522 nanometers. This tells us that the molecule ought to be purple in colour. This was of considerable interest and justified research effort into synthesizing the compound. Eventually the dye was made, and indeed it did prove to be purple. In fact, the experimental wavelength was 524 nanometers, very close to the predicted value. Calculations of this kind are of increasing importance, and dye manufacturers are now using them in the search for new dyes, so saving many man-hours of research. In fact, we can get a lot of other information from this data. For example, about the intensity of the colour of a dye, which is economically important, or about the polarisation direction of the absorption band, which is currently important in the field of dye liquid crystal display devices.
A dye can be made to change colour by changing its orientation in a liquid crystal with an electric field. This is the basis of modern display devices ranging from digital watches to airport destination boards. The computer method is proving of great value in helping to design better dyes for these applications. This is a physical way of changing colour, but of course colour can be altered chemically by causing small changes in the structure of a dye. Acid-base indicators are well-known examples. There's a multitude of commercial applications of this kind, such as analytical chemistry, pressure-sensitive copying paper, and medical diagnosis. In all these instances, prediction of the colour change can be achieved by computer calculation. The action of light can also bring about colour change, an effect known as photochromism. This is used, for example, in photoreprography and in photosensitive plastics. Chemiluminescent reactions give another type of colour produced by light emission rather than absorption. Fluorescence is an example of this, and we're all familiar with some of its uses. Dyes for use in lasers is another important application of fluorescence. Computer colour prediction can anticipate future developments. However, in the important field of pigments and paints, computer prediction cannot yet help fully. Further research is needed. A pigment is a collection of coloured molecules packed together in the form of solid particles. As a result, the colour of each molecule is affected by its neighbours, and the colour of the whole particle is difficult to predict. For instance, different crystal packing of the same substance can produce a different colour. Work on colour prediction has already come a long way and solved many problems. But there's always some new area still to be investigated.
Well, one thing is certain. As long as we humans enjoy the luxury of colour vision, colour chemistry will be there, right at the very heart of technological progress.